Hello everyone, and welcome back to the CS184 discussion recordings. Today we're going to go over discussion 3B, ray tracing and radiometry. So let's get started. So the first topic is ray triangle intersection. So if you guys watched the last discussion, we went over ray plane intersection, and so ray triangle intersection is kind of a more specific version of that, and this will be really useful for when we're trying to render meshes, because meshes are essentially just a collection of triangles. So given the mesh representation, we want to render it to know what parts of the object are visible, where to put shadows, apply the lighting, and all of that. And so let's look how we can do that. So the first step is this ray equation, which we've seen before. So R of t is equal to O plus TD. So O is the origin, the starting spot, and then D is the direction vector. So what direction this ray is moving in. And so then we have a point within the triangle. And so the three corners of the triangle are P0, P1, and P2. And we can represent any point within it using barycentric coordinates. So alpha times P0 plus beta times P1 plus gamma times P2, where alpha plus beta plus gamma is equal to 1. Okay? And so if we use this equation, and we can slightly rewrite it into something like this. So P is equal to 1 minus B1 minus B2 times P0 plus B1 P1 plus B2 P2, where B1, B2 are alpha and beta. Okay, so let's look at the first problem. Let's solve for the intersection of a ray and a triangle. Specifically, if we arrange the unknowns t, b1, and b2 into a column vector, can we write a matrix M and a column vector B so that mx is equal to b? Okay, so let's go ahead and get started. We can do this just by, let's start by just writing out the equation. So up here we have O plus TD is the equation for the position of a ray. Then we have also equation for any point on the triangle, P. So let's write both of these and see what we get. So O plus TD is equal to P0 plus B1 times P1 minus P0 Okay, so the right hand side of this is exactly equation 3, just slightly manipulated a bit. Basically, we just distributed P0 to the things inside the parentheses and then subtracted. Okay, so now that we have this, we can rewrite this a little bit, because remember, we want to get something times t b1 b2 equals something. Okay, so we're almost there. So let's move over the P0 here, so P0, then we can move over the TD and leave everything else on the same side. Okay, and then now, so we're looking something times T, something times B1, something times B2, and that's exactly what we have here on the right hand side, right? So we can massage this and rewrite this into a matrix form. So let's go matrix here. So it's going to be negative D times P1 minus P0, or not times, sorry, P2 minus P0. Okay, so those are the three columns. And then we have our X, which is given to us. So T, B1, and B2. And then we just take this, and that's O minus P0. And now keep in mind that O, D, P0, P1, P2 are all 3D vectors. So this right hand side is a vector, and this left hand side is a 3x3 matrix. Okay, and so there we go. We've done it. This is it. Right there, that's our equation. Mx is equal to b. And just to make it clear, we can write m is equal to negative d, P1 minus P0, P2 minus P0. Okay? Cool. So that's the first step. We just took the ray equation, took a point equation on a triangle, set them equal to each other, massaged it a little bit, and we got this matrix equation. So let's keep going. So now let's derive this Mulder-Trumbore, I want to say, algorithm that you hopefully saw during lecture. So there it is right on the top. equation 4. It's a little bit complicated, but let's go ahead and see if we can derive it. And so we have some hints. Hint 1 is Kramer rules. So given linear equations mx equals b, we can solve them simply using the determinants like this. So that kind of absolute value sign is a determinant. And where mi is the matrix M with its ith column replaced by b. Okay, so m1, m2, m3. And then hint 2, suppose a, b, and c are column vectors. The determinant of the 3 by 3 matrix ABC satisfies this equation. Okay, so now that we have this, let's go ahead and see if we can do this. Okay, so the first step we want to do is, and keep in mind this is our equation right here. This is our mx equals b up there. So we want to solve this mx equals b, right? So we can rewrite this using Kramer's rule as t b1 b2 is equal to 1 over the determinant of m times m1, right? So if we come up here, m is this. So m1 means we're taking this first column, negative d, and replacing it with o minus po, right? Okay, so that's going to be o minus po, p1 minus po, and p2. I don't know why I'm saying po, it should be p0, sorry. p0, and we want the determinant of that, okay? Now the second row, the first column stays the same, but this changes. And then the last one, the first and second column stays the same, but we change that. Okay, so now using just Kramer's rule, we just directly took Kramer's rule and plugged in our values here. And so using that, we've got this equation, right? And so now what we can do is we can simplify this a little. So if we look at right here below equation 4, we have some, E1 is equal to P1, P0, P1 minus P0, all that. So let's rewrite this one more time. So equals 1 over, and so let's go here. M is negative D, P0, P1 minus P0, P2 minus P0. So if we write that down, it's going to be negative D. P1 minus P0 is E1. So E1. And P2 minus P0 is E2. There we go. Then we want to go here. So O minus P0 is S. That's E1 and E2. Then this one is negative D, S, E2, and then negative D, E1, S. Okay, these are all determinants. There we go. Okay, so we've significantly simplified our math. So, we've replaced a lot of these subtractions with just a single variable instead. And so now we have a bunch of determinants, basically. And so what we can do now is we can take a look at this equation 6 that gives us a nice, easy way to rewrite these determinants. Okay? And so what we can do is, let's just rewrite them. So here, this one, the determinant negative D, E1, E2, is if you plug it in, you'll get, and this is, some of this math is a little hard to follow. That's okay. It's not a super big deal if you don't understand exactly how this is happening, since we're mostly just taking advantage of these hints, doing some mathematical manipulation. The more important point is just to understand what we're trying to do is just ray triangle intersection and why that's important. Okay, so if we plug it into equation 6, what we're going to get out here is, and this requires a little bit of math, a little bit of manipulation, so I'm just going to kind of go through it, but this is going to be S1 dot E1, okay, and we do this by plugging this in, so we'd get, negative times negative D cross E2 dot E1, and then that's going to turn into, and basically, here I can just try to write it out. Yeah, why not? Okay, so this is going to be negative D cross E2 dot E1. And then this one is going to become negative E1 cross S dot E2. And then this one's going to be negative D cross E2 dot S. And then this one is going to be negative S cross E1 dot D. Okay, and so now we have these, we have a couple cross products. So if we come back here, we can see S1 is equal to D cross E2, S2 is equal to this. So we can come down here, and what I'm going to do is, because I ran out of space, unfortunately, I'm just going to go ahead and replace. So I'm just going to erase this, right? So D cross E2 is going to get replaced by S1, right? So S1 dot E1, there we go. Over here, E1 cross S is going to go ahead and get replaced. Oh, whoops. There we go. That's going to go ahead and get replaced by S2. Over here, D cross E2 is going to get replaced by S1. And then last but not least, this S cross E1 is going to go ahead and get replaced by S2. Okay, so there we go. 1 over S1 dot E1 times S2 dot E2, S1 dot S, S2 dot D. And if we come up here, you'll notice, let me zoom out a little bit, that that's exactly Cramer's rule. Okay, so we've gone ahead and derived Cramer's rule. Here I can make this dot products a little bit clearer. Nothing too complicated, just using the hints and then mathematical manipulations. Okay, so let's keep going. So 3. Once you've solved for T, B1, and B2, what conditions must be satisfied so that you have a valid ray triangle intersection? Okay, so one of these conditions we talked about last time. So let's start with T. What's the conditions on T? Well, this one's easy. The intersection, like we talked about last discussion, has to be in front of the ray. It has to be in the positive direction. So T has to be greater than or equal to 0. Okay, that's the first nice and easy one. And so for the second one, what we can look is, we can think about what exactly B1 and B2 represent, right? And so if we come up here, we'll see that B1 and B2 are essentially barycentric coordinates, the barycentric weights, right? So what that means is we can say that 0 is less than or equal to B1, less than or equal to 1. Similarly for B2. And then also, remember they must sum with 1, so we can write 0 is less than or equal to 1 minus B1 minus B2, which is the equation for the third barycentric coordinate. Okay, so that's what we can write. There we go. Okay, so these are the conditions that must be satisfied to have valid triangle intersection. If T is not greater than 0, then it's behind the ray, and if one of these other three that isn't satisfied, that means that our intersection is probably not actually on the triangle, but at a point off to the side. Okay, so these are conditions. This is something you probably have to check for in the project to make sure that whatever triangle intersections you're getting are valid. So keep them in mind. Okay, let's keep going. So next up is bounding volume hierarchy. So bounding volumes are really important for ray tracing because they help speed up these intersection tests, and ray tracing is slow as it is, so any speed ups are really useful. So what they essentially let us do is split the entire space of a scene into smaller areas, into a tree of bounding volumes, as it says right there. Right? And so the point is that each bounding volume encloses children bounding volumes, and then in the leaves there are actual triangles that we will test for intersection. Okay, so let's look at how we create one of these so that we can, because you guys will have to do this on the project. So, number one, given a set of planar triangles, build a BVH following these rules. Always pick the longest axis to divide, use the barycenters of triangles to decide their relative positions, and keep the BVH as balanced as possible. Okay, so try to split it up evenly whenever we can. So given this, let's go ahead and try. So, okay, this is the set of triangles we have. Looks like we have, 4 on the right, 3, so 7 total. Let's see how we can split this up. So the first instruction we had was pick the longest axis. And so in that way, it seems it's this way, right? So what if we divided right there along that line, right? Let me shift this up. Okay, there we go. So that's going to split us up into 2 subvolumes. One is, and I'm going to apologize for my drawing right now. It's going to be pretty bad, but it is what it is. Okay, there we go. We've split this up into 2, right? And so now let's work on the left subtree, finish it off, and then we'll go to the right subtree. So we could split this up. Maybe we split this up there, right? Once again, that's the longest axis. And so we're going to go smaller. So now, okay, so this triangle is now on its own. Okay, we've successfully split this up. There's no more splitting to do because there's only one triangle. So if we split it in half, something's going to be empty, and that doesn't help us. So that's done. Let's look at this side, right? We're going to have 2 triangles that look something like that. So we can go ahead, split it right down the middle again, and then we'll have that and that, okay? And so now these are once again done, right? Okay, so that's it. The left subtree is done. We've split it up until we have only one triangle in the leaves. There's nothing more we can do there. So let's work on this right subtree. So we can come over here, and for this one, let's say, I think we should split vertically, right? Because that's the longer axis, so we could split right there. So we're going to have that, and then on this side, we're going to have that, and that, okay? So this one again, now this one's kind of tricky because these 2 triangles are really just right on top of each other. But we can go ahead and split them this way, and we'll get one that looks like that, and one that looks upside down, okay? And so once again, we've come down to one triangle. That's that subtree. And then now let's look at this one. We can, split with something like that so that the barycenters are on opposite sides. And then we'll get something just like that. Okay, and so there we go. We've split this up. At each level, we split in half and keep going until we have only one in all these leaves. At that point, there's nothing more to split, sorry. Okay, and so you will see this again on the project. Over there, we'll be dealing with a lot more triangles, thousands and thousands of triangles. So it won't quite be feasible to get all the way down to, one triangle per leaf. Whoops. But it'll be the same general idea. So keep this in mind for the project, just to have an intuitive idea of what's going on. Okay, let's keep going. So now that we have kind of an idea of how we build these bounding boxes, bounding volume hierarchies, and a really important part is seeing if a ray intersects them, because that's essentially how we decide whether the triangles within a certain volume are important to us. If the ray intersects the volume, then we have to check the triangles inside. If it doesn't, we can just ignore them. Okay, so how do we check intersection with the box? And in specific, in axis-aligned bounding box, what this means is that the sides of this box are parallel to the x, y, and z axes. And so we can define this box given just 2 corners. We don't need to give any more information about it. Okay, so let's look at this problem. So in this problem, we have a box with corners -2, -2, -2, and 2, 2, 2. And then we have a ray with origin -3, 4, 5, and direction 1, -1, -2. So let's see how we can do this, okay? So the general idea is that we're going to intersect this ray with each side of the box. There's 6 sides, 2 in the y, 2 in x, 2 in z. We're going to intersect it with all. Is find out what times it's between the two sides. So in the x dimension, in the y dimension, in the z dimension. And then we're going to find what times it's between all 3 of those, because that's when it's inside the box. Okay, and so the general formula for finding an intersection with the side is going to look something like I is equal to, so I'm going to put P for the dimension of this, or the position of the side, minus O over D. Okay, and so this is just in one direction, and basically all it's saying is P minus O is the difference, the distance from the side of the box to where you start. D is how far this ray moves in one step, and so I is just going to be, well, how many steps does it take to hit this, right? Very simple equation, nothing too crazy. So let's see how this actually happens. Let's start in the x direction. So the time of the first x intersection, we're going to take, so -2 for the position, right? That's one side, minus the origin, so that's -3 all over 1, right? And so that's going to be 1 over 1, 1. Then let's look at the other side, so tx2. Now this time, instead of -2, we're going to look at 2, right? That's the other side. Still -3, that's still the origin in the x, still 1, and so that's going to be 5. Okay? Now, let's look at the y. So ty1, right? Now we have -2 minus 4 all over -1. So that's -6 over -1, so 6. And then this is ty2, and so that's going to be, once again, oh no, sorry, it's going to be 2, because we want the other one, minus 4 stays the same, -1 stays the same, and that's going to be 2. Okay, and then last but not least, tz1 is going to be -2 minus 5 over -2, right? So that's going to be -7 over -2, so 3.5. And then the last intersection is equal to 2 minus 5 over -2, right? So that's going to be 1.5. Okay, so what does this mean? We have these numbers. What do they actually mean? Basically, if you moved in the x direction, just purely in the x direction, you only looked at the x-axis, there is a range within which you'd be within the box in the x dimension, right? And so actually here, let me do a little bit of a drawing. So let's say, whoops, okay. Let me do it down here where I have space. Let's say this is the box, and this is x, and that's y, right? So from here to here, all this region, we're within the box in the x direction. And from here to here, we're within the box in the y direction, right? So if I get rid of that, so if we have a ray that comes in here and goes that way, when it intersects this side, that's when it starts being within the box. It intersects here. And when it intersects here, that's when it stops being within the box, right? And similarly, when it goes here, it starts within the box, but when it intersects this side, that's when it stops being within the box, right? The bottom corner. And so essentially, these timings are telling us, the lower time is telling us the first time it's within the box, and the higher time is telling us when it leaves the box. Okay, so in the x direction, between t equals 1 and t equals 5, we're within the box. In the y direction, between t equals 2 and 6, we're in the box. In the z, between t equals 1.5 and 3.5, we're in the box. Okay, so this is great. We know when we're in the box in each direction, but that's not really what we're here for. What we want to know is when we're in the box in every direction. Okay? And so the way to do this is, in order to be in the box, so we want to know when we're in the box in all 3. So what we do is we take the max of the mins and the min of the maxes. Okay? And so the reason for this is, so it's going to be basically the max of 1, right? That's the minimum x value, 2, and 1.5, right, which is 2, and it's going to be the min of 5, 6, and 3.5, which is 3.5. And so the reason we do this is because, let's look at t equals 2, right? X goes from 1 to 5. So yeah, we're inside the box in the x direction. And z goes from 1.5 to 3.5, so we're in the z direction. But y doesn't. At 2, we're only intersecting, so we're not there, right? So essentially, we want to check the range of overlap between all of these, and that's the max of the mins and the mins of the maxes. And so essentially, we know that we're in the box starting at t equals 2, and we leave at t equals 3.5. Okay? And so if we want to find the actual entry and exit point, we just take these times, plug it back into the O plus TD equation. And so I'm not going to actually go through and do the math right now. It's quite simple, but it's going to be entry is -1 to 1, and exit is 0.5, 0.5, and -2. Okay, so that's how we do intersection with the bounding box. You all will have to implement this in the project, so it's good practice, and keep in mind. All right, let's keep going. So the next section is radiometry and photometry. So when we're ray tracing, the units of light transport become really important, because that's essentially what we're simulating. We're simulating light bouncing around our scenes and light going into our eyes, which is how we see. Okay, so the first problem is just talking about some units. So what's the difference between radiant flux / power, radiant intensity, irradiance, and radiance? And how does increasing the distance from the light source affect these values? So if you want a detailed explanation for all these, look at the lecture. The lecture slides will have it. I'm sure it was discussed in lecture, and that's the best way to learn these. I'm just going to go over it really briefly here, just talk about it, and then, but look at the lecture for more details. So radiant flux or power, phi, is the energy emitted, reflected, transmitted, or received per unit time, okay? So I'm just going to go ahead and say energy per time. Remember, emitted, reflected, transmitted, or received. The radiant intensity, so I, is the power per unit solid angle. So power per unit solid angle emitted by a point light source. Okay, that's radiant intensity. The irradiance E is going to be power per unit area, power plus area, and then the radiance L is going to be the power emitted, reflected, transmitted, or received by a surface per unit solid angle per projected area. So it's going to be power per solid angle per area. Okay, so these are all 4 different units. They involve 4 slightly different topics, but all related to light. Okay, and so now let's look at this next question. So how does increasing the distance from a light source affect these values? Okay, and the answer is that the only one affected by increasing the distance is the irradiance, right here, E. Okay, and let's see why. So first up, let's look at radiant flux. So that's the energy emitted, reflected, transmitted, or received per unit time. And so as we examine these, the best way to think about this is, let's say we had a point light source and a sphere around it. Okay, and we look at how much power or energy is hitting the sphere. Well, no matter if we move this, increase the radius of the sphere, move far away, it's going to be the same, right? The energy being released, hitting the sphere, is the same. So radiant flux stays the same. Now let's look at the power per unit solid angle, right? So once again, as we increase the sphere's radius, this will also remain the same because of the per unit solid angle, right? The sphere will always have the same 4 pi steradians, but so this is going to stay the same. The power per unit solid angle, same power, same solid angle, so it's going to stay the same. Now let's look at irradiance, right? It's the power plus per area. So as we move this sphere outwards, as it gets bigger, the amount of power leaving the light source is the same, but the area of the sphere increases. So the area on which the same power is hitting increases, which means the irradiance will decrease. So that's going to change. And then lastly, the radiance is the power per solid angle per area, right? And so this is basically how much light is flowing per ray. This does not decrease over distance, right? This because the ray can go as far as it needs to, but we'll just have fewer rays, and so this also stays the same. Okay, so those are some of the units. Once again, look at the lecture for more details on that. Let's keep going. So number 2, suppose we use a theta phi parametrization of directions. Recall that solid angle represents the ratio of the subtended area on a sphere to the radius squared. Omega is equal to a over r squared. Estimate the solid angle subtended by a patch that covers, so theta is pi over 6 minus pi over 12 to pi over 6 plus pi over 12, and phi is pi over 5 minus pi over 24 to pi over 5 plus pi over 24. Okay, so let's look at this. So first of all, remember we want to talk about differential solid angle d omega, right? And so we have omega is equal to a over r squared. So d omega is equal to dA over r squared, right? And so let's look at this to find out dA. Let me change this to red. Okay, so this little black box is the area we want to look for, right? And so what is that going to be? So the top of it is given to us already. Look, it says r sine theta times d phi, right? Because that's the equation for the length of an arc. It's the radius times the angle. So it's going to be r sine theta times d phi. That's that right there. And then meanwhile, this side is going to be d theta, right? That's because we're in the theta direction, times r, because that's the radius of the circle. So that is r times d theta, right? So if I zoom out again, what we can do is this will become basically r sine theta d phi times r d theta. Okay? Which is equal to r squared sine theta d phi. But keep in mind that we have this r, we're dividing by r squared. We have that hanging out on the bottom. So this is all over r squared. So this is going to go away. And what we can do is write d omega is equal to sine theta d phi. All right. And so now once we have this, it's not very hard to write at all. We simply plug in some values. So that's equal to sine. Now what's theta given to us? Look, pi over 6, right? D theta is the difference in theta, right? So we're going from minus pi over 12 to plus pi over 12. So if we do the math, that's going to become 2 pi over 12. And then d phi, we're going from minus pi over 24 to plus. So it's going to become 2 pi over 24. Sorry, I ran out of space a little bit. So that's going to be equal to 1/2 times 2 pi over 12 times pi over 12, right? Because the 2 and the 24, these two will go. So it's going to be pi over 12 times pi over 12, or pi squared over 144. Okay, so there we go. That's our, we're looking for the solid angle. So that's going to be it. Okay, there we go. Pretty simple. We went ahead, derived the equation for the differential solid angle from the normal solid angle equation, and then just plugged in some values and got our answer. Okay, let's look at number 3. So, okay, sorry I covered it up a little bit, but I'll read it. It says calculate the irradiance at point P from a disk area light overhead with uniform radiance L. Hint, a radius is an integral of incoming radiance over the hemisphere. And there's an integral equation. And so here's the drawing on the side. There's the light up top, the point P. So let's set this integral up, right? Well, so okay, let's look at this. We're integrating over the hemisphere, right? But we're interested in where is the light actually coming from. And so the light is coming basically along this cone, right? So let's write this. So what we could do is this d omega here, right, just above, we found that d omega can be rewritten as sine theta d theta d phi. So let's change the parameters here. So it's going to become E of P. So we're going to have 2, right, because L cosine theta sine theta d phi, right? And so this is all coming from the d omega. We essentially changed from d omega, used this change of basis to d theta d phi, and so that's why we have the double integrals now. So let's see, what should the limits on the integral be? So phi, well, we're going all the way around, right? We're taking in the whole hemisphere, so that's going to be, phi is going to go from 0 to 2 pi, right? Easy. What about theta? So theta, if we look at this normal, right up there, and then we go till there, right? Because after that, we can't see anymore. So that's it. So it's going to be alpha. So we're going to go, so theta is going to go from 0 to alpha, and phi is going to go from 0 to 2 pi. And so let's go ahead and do this. Let's go ahead and do the math, okay? So nothing inside the integral actually relies on phi, so we can just go ahead and pull that out. L is a constant that can also come out. So we're going to get 2 pi L times the integral from 0 to alpha of cosine theta sine theta d theta, right? And you guys can go ahead and plug this into a calculator, an integral calculator. That's not a big deal. I'm just going to go ahead and give you the answer. So it's going to be sine squared theta over 2 from alpha to 0, right? Sine of 0 is 0, so that part is gone. And we're basically going to get E of P is equal to 2 pi L times, so actually this 2 pi is going to, this 2 is going to go away because we have this divided by 2 here. So it's just going to become pi L sine squared alpha. Okay, and that is our answer. So we had this integral that was given to us. We took this d omega, changed it into a sine theta d theta d phi, so it changed up the integral into a double integral, found the limits, and then just integrated out, and we got our answer for the irradiance. Okay, so that's all for this discussion. We went over some ray tracing, bounding volume hierarchies, and some radiometry. Look forward to see you next time.